So, hi, I'm Robert, and I'm happy to be back here. I was on the spring meetup, and I also visited the town when I was visiting family in my youth, so I have roots here. But let's get to the technical side of things. Well, introduction first. So I started writing programs when I was about 9 years old, became a professional software engineer, and now I write software for hydroelectric power plants. I have about 15 years of experience with C++ and Qt mostly, and my specialization is visualization and UI. I used to do all of that myself. Now I split time doing the juicy coding myself and helping some junior developers getting their work done. And surprisingly, the juniors are not named Gemini or Claude yet. Okay, I also co-founded the C++ user group Vienna. So if you ever go to Vienna, please check us out, visit us, join our event. There is a lightning talk session on December 16. So if you're interested, please let us know. So over the years, I have solved similar problems more than once. And this has showed me how my own coding style evolved over time. So when I see a piece of older code, I always ask myself, how would I write this today? So imagine you are me, and you have just stumbled over this piece of code here. Now, I'm not looking for in-depth analysis, just give me your gut feeling. Who likes this style of code? And who does not like this style of code? I think we have a majority here. I don't like it either, and I'll tell you why. It interleaves the core functionality with error handling, making it really hard to see at a glance what the function does. In addition, we have this bool return value, which is actually a success flag, and the actual return value is at the end of the parameter list, and we're not going to mix those two up, are we? Okay, we could use exceptions, of course, and then it might look something like this. We need to throw somewhere, and we need to catch somewhere, and of course, if we don't catch the right exception, we crash. And also, I found out on Windows exceptions are really slow. I don't know why. And should we use exceptions for domain errors? I'm not sure about that. So let's go back to step one. Maybe we could do something like this. We just make an error flag a class member. Now every function can simply read from it and write to it, and looks good. Not really, because we just moved the checks around. We have not solved the problem really. And congratulations, we have created our own little dependency hell. Every function now depends on this single error flag. And this is called shared mutable state, and it's poison for thread safety and local reasoning. So let's take a step back and fix the return type issue first. And we can combine the success flag and the actual result into an optional of the result type. There's no ambiguity anymore. If the optional is empty, that implies failure, and if it holds a value, we can use it. And then we throw away all of our if statements and let optional do the work for us. This way, the sequence of the function is plain and clear to see. We also cannot forget about the error handling because optional does it for us. This is a monadic operation in action. I set myself 3 goals for this talk. First, I'd like you to understand after the talk what functors and monads do. What they do, not what they are. It's not about theory, it's about practical usage. Second, I want you to be aware of the monadic operations in the standard library and able to use them without much trouble after the talk. And finally, if you get curious and you want to know more about this, I will give you a lot of leads and references to follow up on. All the code that you see on the slides is available on the GitHub. I will share the link at the end of the talk, both for download and as Compile Explorer links. And please keep in mind the code that you see on the slides is slideware, const removed, other stuff. So please, when you want to play around, use the code from the GitHub or from the Compile Explorer. And did I mention I have children? well, I was able to get rid of the dinosaurs, but there might still be unicorns hiding in these slides. Okay, I promised monads now I talk about functors. And why is that? So every monad is a functor, and functors are simpler than monads, so it makes sense to explain functors first and then move on to monads. And if you now say, I know what a functor is, that's this call operator thingy, you're not wrong, that's named a functor, but this is not the functor we're looking for. So what are we looking for? Let me start with a little story. Once upon a time, there was a little sequence of code. It consisted only of two functions. One, to calculate the area of a circle based on the radius, and the second one to format the area nicely as a string. They were combined, so you could pass a radius and get the formatted string of the circle's area, and everything was good. Then a developer came, and she brought a vector of radii. And naturally she wanted a vector of strings. No problem, they said, we'll just make a loop. And inside the loop, we will pretty much do as we did before. But then one of the functions said, this does not feel right. I'm sitting here together with code that knows nothing about circles, areas, formatting. It has nothing to do with me. I'm afraid we have violated the single responsibility principle. And when I asked the seer what he sees in the future, he said, code duplication. How much better would it be if somebody could magically transform a poor function so we can handle a vector? Like, maybe we create a new function from the old one. And we pass the old function as a parameter. Then the new function would accept a vector of whatever input the old function accepted and would return a vector of whatever output the old function returned. So, for example, for format area, which accepts a double and returns a string, the new function would accept a vector of double and return a vector of string. Now we can combine those two new functions and handle vectors. The vector aspect is only implemented once. This is one way a functor can look like. I would like to show you a different way that's maybe more like what we are used to. Let's think about it as a container. In this version of a functor, the class holds the data that it wants to transform. As we've seen before, this is not necessary for it to be a functor, but it's sometimes convenient. In this kind of functor, we pass the function to transform data into a member function that will apply to all the items in the vector. And the result is a new functor with the new data, so we can immediately repeat the process. Again, the vector aspect is only implemented once. So we've seen two approaches. Both are functors and both solve our problem. But let's take a look at what a functor does conceptually. So on the one hand, we have what I would call a category of single values: radius, area, formatted string. And we have the functions to go from one to the other. On the other side, we have a category of what I would call vectors, of things like radii, areas, formatted strings. Now, what we want is to go from one to the other in this category of vectors. And we can do that by stealing the function from the single value category, and applying it to all items in the vector. And this is where the functor magic comes into play. And then we can just repeat the same process for the next stage of the pipeline. And the nice thing is we don't have to stick to vector. We can just replace it by optional. Our functions don't need to change at all. This is nice single responsibility principle in action. Now let's add a little theory, because every functor has to follow two rules. The first rule is the rule of composition. Because what we can do is we can compose our functions into a single function that directly takes a radius and returns a string. And naturally, we can apply this function via our functor and should get a vector of strings. And it has to be the exact same vector as if we applied if we went through the pipeline step by step. The second rule is the rule of identity. It says that identity has to be preserved. This time we use a different function, std_identity, which takes an argument and returns it unchanged. Now, of course, I can apply it via a functor. I have a vector of radii, I should get a vector of radii, nothing changes, and it really has to be the identical vector, which means the functor cannot use internal or external state to influence the result. It can only use the function we give it. So to summarize, a functor provides a mapping between different categories, like from single values to vectors to optionals to other things. And this mapping has to preserve composition and identity. And as we have seen, functors can be implemented in different ways. And this implementation does not make it a functor. It's the behavior and the characteristics and following the two rules. Now, I used vector as an example to show the benefits of using a functor, but of course we might not want to use vector all the time. We want to use any range. And also we don't want to write such a functor ourselves. We don't have to. It's called std ranges views. When we look back at the vector example, specifically at the classical implementation, we can get pretty much the same with the code below. Let's see how it works. Here we have a function, std views transform, which takes two parameters. First, the input data, the input range, and then a function used to transform the items to something new. The output is a new range, so we can immediately plug it into the next transform call. Now, this notation with the inner and outer transform is pretty confusing, so the pipe operator to the rescue. This way, we have a much more natural representation of a pipeline, and this is how it works. So here we start with our input range, a vector in this case, and basically it kind of inserts itself into the transform function. So the first transform function applies to the vector that I started with, and then I can use the output in the next transformation. Now there's two questions here. What do we actually return? And what type is the view? Let's answer the second question first. Because what we get is not a container and it does not hold the results. Think of it like a recipe for cake. It's not a cake, but it tells you how to get there. It also typically does not own the data. If somebody steals your ingredients while you're looking at the cookbook, that's undefined behavior. Well, or at least there won't be any cake. And it's also typically lazy. That means that the data will be evaluated when you need it, not when you define the pipeline. And this is the view in this specific example, and it varies by compiler, so you have to use auto. And this has some implications. When we return a view from a function, we have to use auto, which means the compiler needs to see the definition of the function to know what auto means. So we cannot separate declaration from definition into separate files. But then again, it's also not a function template because only the return type is auto and it's actually well defined. We are just too lazy to type it. So what I recommend, mark such functions inline, don't overuse them, and keep the scope small where you use them so you still see where the lifetimes are of the input that you are using. We can also return a container, and that's really easy with C++23. Std ranges 2 converts a range into a container of our choice, which can be a standard library container or a third-party library container that supports the interface. What we lose in this case is the laziness, because we have to evaluate all the data in this one line, but we can separate declaration from definition again. So to summarize, views are more like a recipe, it's not the cake. They typically don't own the data, so be careful about lifetimes, use auto, and they evaluate lazily. And they are traps. I mean, of course, we're talking C++ here. So depending on compiler, build settings, and so on, this will crash, output garbage, or maybe even work. Let's walk through it quickly. So we have a simple struct with 2 integers and 1 string, C entry. Then I have a function getNearestEntry, which takes an integer and returns a C entry by value. Implementation doesn't matter. So what we want is we want to go from integer via C entry and finally get the string out of the item so we can print it. So in the first transformation, we use getNearestEntry to go from integer to C entry. Awesome. And then we just use the members because we just want the string. But this way, we have a dangling pointer, a dangling reference, because the C entry was just a temporary and it goes out of scope. It's like a function where you pass something by value and then you return a reference into that object as a return value. Of course, the function is much more obvious. The pipeline is maybe a bit more hidden, so be careful and always use a sanitizer. As you might have noticed, passing callables is an important part of using functors, and the same applies to monads. When I started this coding style, I often had difficulty finding the right ways to adapt my functions so they fit into the functor of my choice. I want to spare you some trouble and show you some ways to do that. We can use free functions, and that's pretty easy as long as they don't have any overloads. We'll come to overloads in a moment. You can do the same thing with static functions of classes. And then you can have an inline lambda, which just is a piece of code that you want to execute there and then. This is useful if it's a little code, if you don't want to reuse the code, mostly. I mentioned issues with overloaded functions. So if you have an overloaded function, the compiler cannot figure out which one to take, and usually wrapping it in a lambda does the trick and suddenly it compiles. There's another typical issue. Let's say I have a function with 2 parameters and my functor will only provide one of them. Well, use the lambda capture for the other parameter. Then I might want to call a member function of an object. So in this case, the functor gives me an object instance and I want to call a specific member function on that object. Again, lambda is great for that. Another way to use a lambda is if it's the other way around. The functor gives me a value and I want to call a member function of a known object instance with this value. So here I pass the object instance via capture list. We can use lambdas multiple times, which is sometimes useful for documentation or if you really want to use it multiple times. And then we can also write function objects ourselves. Basically very similar to lambda, but it gives you a little bit more flexibility. And then there's a very interesting option. You can inject behavior. And one very easy way to do that is using std_function. Std_function wraps any callable that fits a certain pattern, that has a certain signature, and the signature is in the template argument list of std_function. So you specify return type and the argument types. And this way you can get this std_function from somewhere and just plug it into your pipeline. So you can have a pipeline and the user can say what should happen on stage 3 of the pipeline. Of course, you can also do that with templates. You can pass a callable as a template argument. And if you want to make sure that it's a callable that fits a certain signature, then you can use the std_invocable concept. Now, both ways are valid. Std_function has a little runtime overhead. Templates typically make your code a bit more complicated. So as we've seen, there's many ways to feed your functors, and lambdas are very flexible, the Swiss Army knife, I would say. And add std_function to inject behavior and you have a really good basic set. Now that we know what functors are and how to feed them, let's talk about monads. Because monads, as I mentioned, have all the properties of a functor plus something extra. But let's start again by seeing how a monad helps us solve a problem. In this example, we have, let's say, a tree-like structure, and we have a node. And node has a function getChildren. Doesn't matter how exactly that's implemented. It's only important I get multiple children. So let's say I get a vector of children. Now, if I want to get the grandchildren, that doesn't work because getChildren doesn't know how to handle a vector of inputs. So let's try the functor trick again. So we start again with a vector of nodes, and then we do our functor magic, and this gives us now a vector of nodes. Oops, I think Transform is not going to be happy about that. So what do? We invoke monad magic and flatten the vector, removing the nesting, and that allows us to continue. And we can do the transform again, and we can do the join again. So for our practical purposes, a monad is a functor with the ability to unwrap levels of nesting. This is very hand-wavy, but it's enough for our practical purposes here. So what you typically cannot do is unwrap the last level of nesting. Since monads are functors, the rules for composition and identity still apply. And as we will also see, transform and join are often combined into a single function that differs by name. Now let's leave theory behind and look at examples. It has been said that a compiler is a tool that takes files as input and produces diagnostics as output. Let's now ignore the fact that it might also produce an object file or something like that and focus on getting and printing those diagnostics. And let's start with a function that can print a single diagnostic. And then we have a function that will compile a single file and give me, of course, a vector of diagnostics. Would be boring if we had only one. And then we might want to compile multiple files. So I added something called get files in project. Doesn't matter how exactly that works, but it will give me multiple files. And this would be the classic style loop for it. So we loop the projects, we get all the files in the project, we loop the files, we get the diagnostics of a single file, loop the diagnostics and print them. So who uses code similar to this one? Not that many. I think my people at home are old-fashioned. So how would we do it in a more monadic fashion? So with split ranges view, we start with the projects. Then we transform them into files using the get files in project function, which gives us now a vector of files. So we have to join and flatten it. Then we pass it on to compile, which now gives me a vector of diagnostics. So again, we flatten and join, and then we can loop and print. So here are both versions side by side. Which one makes the intentions of the author clearer? Now the question is, do they behave differently? In effect, no, they call the same functions in the same order with the same parameters. I cannot say that about performance. I will talk very briefly about that at the end. But let me now sidestep a little and talk about the topic of using functors and monads, and specifically ranges views, in a safe way. And in my opinion, pure functions are a key to that. Who knows what a pure function is? Okay. For all the others, I will explain in a couple of minutes, but let's start again with a motivating example. Here we start at the bottom with a vector of numbers, and what we want is a view where all these numbers are multiplied by 2. So I have a function above which accepts my input range and a multiplier, and inside the function I have a little lambda which will handle a single item, and we get the multiplier by lambda capture. And then we just return a transform view. And back at the calling function, we print the output. It doesn't really matter how. So what do we expect? We start with 2, 4, and 6 times 2. That's of course 4, 6, and... Okay, I think we have a bug here. Okay, let's think this through. So we first pass the multiplier by value. I guess that's okay for an integer. And then we capture it by reference. Ooh, okay, is there something going on? And the transform is lazy, which means it will execute our lambda when we have already left function scope, and the multiply is a dangling reference. Now, this example was for state ranges views, but in general, when you're using functors and monads, you have to be aware that they control when you get called, how often you get called, and in what context you get called. So how can you avoid bad usage of your functions? I see mainly two choices. You can study the fine print and the guarantees that the functor monad gives you and hope they don't change. Or you can make your functions safer by making them purer. And I want to look into this option. So what is a pure function now? It has mainly two properties. It will give you the same result for the same input, and it has no side effects. Okay, what does that mean? Let's say we have a function with some inputs and an output, and assuming you had infinite memory, can you replace it by a lookup table? And if this is possible, then we're good on the first requirement. And what does no side effects mean? It means we're not writing outside of our own stack frame, and we're not triggering other side effects such as I/O. Pure functions have a lot of advantages. They're easy to reason about because you just have to look at the function to fully understand it. You don't have to keep any global state in mind. It's easy to write unit tests for them. You can use the lookup table approach, maybe a piece of the lookup table, to verify whether the function behaves as you expect. And also, if it's really pure reading and writing, then it's inherently thread safe. Pure functions are useful in combination with functors and monads, but they are also valuable on their own. So let's say you have a complex function which interleaves complex logic with side effects. These are typically hard to unit test. So what I like to do is like to split it into a pure function which has as much of the logic as possible, and a relatively simple execute function which handles all the side effects. Of course, it takes the data from the other function. And then I might make a wrap around it so to the outside world nothing has changed. Now, the pure function is easier to unit test because I can use the lookup table approach. And even the execute function is typically easy to unit test because now I have a dedicated API to trigger specific side effects. All right, let's have a little quiz here. I will list some functions from the standard library and you tell me whether you think they are pure or not. And let's start with stdmax with integer and no custom comparison. Who thinks this is pure? And who thinks this is not pure? Yes, this is pure. Stdfill for filling ranges or containers. Who thinks this is pure? And who thinks this is not pure? We are writing to memory outside of our own stack frame. That's not pure. Next is std chrono system clock now. Who thinks this is pure? And who thinks this is not pure? Well, good luck writing a lookup table for that one. Next is stdsyn, calculating the sinus of double. Who thinks this is pure? Who thinks this is not pure? So this is interesting because it actually might depend on the implementation, because some use global rounding modes. Then it's not pure, not really. Last is stdapps, calculating the absolute value of an integer. Who thinks this is pure? And who thinks this is not pure? Well, what do we do with int min? It's undefined behavior. So can we say it's pure? Otherwise it is. I don't know. So what I wanted to point out with this quiz, it's not a black and white thing. There is some gray areas in between. And while pure functions help us write safer and reliable code, it's often really hard to make a function completely pure. So I take the practical approach and make it as pure as is reasonable for your use case. And looking back at our example, we could argue that one of the problems is that the lambda is depending on outside state. And we can improve that by making the capture by value. Is it now completely pure? I actually don't care. It fixed the problem. Okay. In the example so far, all the functions did not have to handle any kind of error situation. And as we know in real life, that's exactly how things work. Not really. So we have to be able to handle failure of some kind. And if you don't want to use exceptions for whatever reason, let's say because it's a domain error and not, let's say, out of memory error, then you need other options. And in this section, I compare the classic return a bool success flag approach with still optional and still expected. So let's say we have some kind of data structure. It doesn't matter how exactly that works. It contains very different data. So trends, images, and tables. And looking more closely at the table, we can identify a column via key or index, and we can do the same with the row. And that gives us a cell, and we can now ask, does this cell contain a number? And if it does, we can check, is it negative? So this is what we want. We want to know whether the value inside a table cell is negative. What could possibly go wrong? Well, the database key might be invalid. It might not be a table. The cell might be out of bounds. It might not hold a value. Well, and if it does, we can check if it's negative. So this would be a classic way to implement this. And we start with a function called getElement, which we pass a database handle and a key, and we receive an element as parameter, as reference parameter. And the return value, the bool return value, is just a success flag. It tells us true, succeeded, false, failed. I see those a lot in old code, and I hate them because you cannot compose them well. But yeah, that's what we have. So let's continue. Get table. We extract table data. And again, the bool return value indicates success or failure. Get cell needs an extra parameter for the cell location. And then we have to get numeric cell value, which returns an integer if the type is correct. Does anybody have a flashback? So this is how we call the functions. We create C element on the stack and ask get an element nicely to fill it. Then we check and we exit early on failure. The same with get table, create on stack, ask function to fill it, early exit on failure. And for the cell and for the integer value. And finally, we are in success area. We can check whether the value is negative and return with success. Who has code similar to this one? Okay, how would we do it in a more declarative monadic fashion? So we change our interfaces. Instead of returning bool, we return an optional of whatever type we want returned. Now, optional wraps a value, and if we fail, we just return an empty optional. And if we succeed, we return our value wrapped in an optional. So we do the same for get table, get cell, and get numeric cell value. And for the sake of completeness, I also added a isNegative function, which of course is not strictly necessary. But the interesting part here is I don't return an optional of bool. And the reason is this function itself cannot fail, so I just return a bool here. And then we start our chain of operations with getElement. And getElement returns an optional of C element. And the nice thing is we can now call the next stage of the pipeline conditionally. That is, only if the element holds a value. And to do that, we call endThen. We pass the operation that we want to be performed next as a parameter. And the result is a new optional of the new type with the correct type. And it contains the transformed value or it's empty, depending on whether we succeeded or failed. Since we're talking here about values that may be there, it's also called the maybe monad. So let's assume get table was fine and also get element was fine and also get table succeeded. So we have a table in our optional. And now I don't see any join here. Why do I call this a monad? And let me remind you of the function interfaces that are involved here. Maybe you noticed something. Because getElement returns an optional of C element, but getTable does not need to take an optional of C element. We have somehow stripped away the optional on the way, So we have unwrapped one level of nesting. And what happens is that end then is exactly the function I talked about. It combines join and transform. Okay, back to our code. We pass the table and into getCell. And getCell needs a second argument, so we pass the location via lambda. And let's assume it was a bad location, so our optional is now empty. And because of that, the next function, getNumericCellValue, is now bypassed. We still get an optional of integer, but it's as empty as the input was. And finally, we have isNegative. And isNegative does not return an optional, it just returns a bool. So here we have to do something different. We have to use transform, similar to like we did in views. Again, it will only be called if the optional holds a value. So what can we do with optional? Basic operations is we can check if it holds a value. We can access the value. If we do that on an empty optional, it will throw an exception. We can simplify it by moving the assignment into the if block. Then we can assign and check at the same time. And if all we care about is a fallback value, in case the optional is empty, we can also use value or. So here's a comparison. Classic way on top, monadic way on bottom. Let's have a little poll. Who prefers the classic way of code? Who prefers the monadic way? At home, I actually had some hands for the classic version. Okay, but so it works. But what about logging? Let's say we want to log in case something failed. So and then has a sibling function called or else, which works exactly in reverse. It will only call our function if the optional is empty. Since empty is the indication of failure, we can use that. And why is it a function template? Because it has to return an optional of the correct type, and it cannot otherwise know the type that it's expected of it. So I just pass it as a template argument. Now there's a problem here. Let's say we have an error in getCell, and we can catch the error. So we know that an error happened, but we have no context. We don't know where the error happened, what error happened. We know nothing. So there must be a better way to do this. And there is. In C++23, we have setExpected. So what we do, we change our interfaces. Instead of optional, we return setExpected. Now expected has two template arguments. The first one is the value, like in optional. Now the second one is error information. When a function now fails, it returns an unexpected, and it returns error information. So here I created a custom error object that takes a message in the constructor. And we can also use the C++23 stack trace library to dump a call stack at this point, so we know exactly where the error happened. Please look it up if you're interested. So if everything's okay, we return a value like before, and the chain is exactly identical. And then behaves the same way, so it will call the function if the expected holds a value. And if an error happens, we now have error information inside the expected, which means that we will bypass the next function and retain the error information. And at the end of the chain, we will capture this error information in or else and can do some useful logging. So here we see the log function, and it now gets the error info as parameter. So for example, if getCell fails, it writes the error location, it writes an error message, and this is transported down to our log function. We also have another option. We return an expected. So we can choose whether we want to just pass through the error information. We might want to amend the error information, or we could even return a valid fallback value. Although I would probably not do this in a log function. Usage is similar to optional, so we can check the value, we can access the value, and now alternatively we can access the error information. Expected always holds either the value or the error information. We can again check directly on assignment, and we can also use value or to fall back to a default value. Error or exists as well, but it's small use cases, I think. Finally, you might want to convert the arrow type. And all you need to do is expected transform arrow function and a conversion function that you provide, converting A to B in this case. We've seen how we can use optional and expected to ensure that in a pipeline all functions succeed. Otherwise, we get an error. But sometimes we want the exact opposite. We want to go through a list of functions and we want to grab the first result that we get. And this is easy to do with optional. So here, let's say we have an application, we start it and we want to set the UI language. And we have given the user 3 ways to define it. They can set it via command line. They can do it in the registry or a similar system. They can set an environment variable. And if nothing is set, we have a fallback value. And this is the pipeline. In this pipeline, the first function that has a value wins. So let's assume that getLanguage from command line failed. Our option is empty. Because of that, getLanguage from registry will be called. Now let's say it succeeds and we have a value in our optional. Because of that, the next function is bypassed and we keep our value. Had we been empty at this point, the value OR would have provided us with the default value. Now, maybe somebody noticed that I put monad in quotes in this section. And there's a good reason for that. Let's again consider the dimensions that we're moving in. So we have the transform dimension, what a functor gives us, which allows us to go from optional of A to optional of B to optional of C. And then we have the join dimension, which allows us to unwrap nesting. We can go from optional of A to optional of A. Of course, we don't have a join function with optional. What we do in optional is we move diagonally across this table with end then. And what does it have to do with or else? Nothing at all. With or else, we start with a type, we stick to the type, we don't move across this table. This is not a monad. We could maybe call it a monadic style operation, but it's useful, so I included it. So, I've talked a lot about how great functors and monads are. Now, is everything pink unicorns and rainbows? Somehow life does not work that way. So, this is the first thing that's going to greet you, nice compiler errors. Something like this here. And yeah, maybe AI can fix it for you and just fix the error for me. I don't know. I haven't tried yet. But let me give you some first aid in case you want to do it yourself. So first recommendation is focus on beginning and end of the compiler error first, because this is where often very useful information is hidden. And then you can go through some common causes for errors and rule them out, such as function overloads, which we mentioned in the callable section. So if you have a function that's overloaded, the compiler cannot figure out which one to take, wrap it in a lambda, and it usually works. The second thing is that you might be accepting or returning the wrong type, such as optional of t instead of t, or vice versa. And what I found is it helps if you make types explicit also in lambdas, because there it's very tempting to just write auto, but it actually helps in diagnosing if you have the type explicit in the lambda. And then you might try to pass views as const or const reference. Just don't do that. They are not designed that way. You can find a compiler error cheat sheet on my GitHub, which I will share in a couple of minutes. And then we move on to debugging. And it's unpleasant. I mean, few people I know love to step through half the standard library to connect the dots between function A and function B. So, what would we need for a good debugging experience? So we start somewhere, let's say where we loop over a view. And then I would like to see the pipeline and in which stage of the pipeline we are. And then I want to see this function that gets called in that stage, and I can step through the function, see what it does. And we can have the first one and the last one. The last one is easy. We just need a breakpoint, but we lose the connection. So what do we do? Let's take a step back and think about why are we using a debugger. And I mean, it has different uses, but one of them is to find and eliminate bugs. But there's other ways to do that. What do we have? We have code that consists of multiple individual components bound together in a pipeline, and each of these components is ideally pure. This is a unit test stream. So what I would recommend is write unit tests for each component individually, find the one that doesn't conform, fix it, and bind them together with strong types, which makes it almost impossible to construct a pipeline that is incorrect by itself. And then you check it into your CI and stop worrying about this type of bug. But I mean, I admit it, sometimes I also like to do some interactive debugging. So what can you do? You can debug the individual components, no problem about that. What you have to do is you have to prepare yourself mentally and look at the pipeline to see how things are connected, which you cannot debug, but at least it should be readable code. And then there's performance. I made a couple of benchmarks. They are also on the GitHub, and the results vary widely by compiler, by topic, and so on. The truth is, if you need the last nanosecond of performance, you have to write your raw loops. You have to worry about cache friendliness. You have to use SIMD probably and other things. But how often is that the case? I mean, when I have a function that waits for user input, that opens a file, that waits for data over the network, do I really need to worry about the last nanosecond? I mean, only you can know for your use case. So please, in my code, I know that the majority of functions are not on a hot path. And there it really doesn't matter whether I use raw loops or ranges and views. So please look at my results, make your own measurements, draw your own conclusions, and then decide whether it's worth to invest the more complex code for performance. And sometimes that will be the case. I believe it's important that you know both the advantages and the disadvantages of using functors and monads. So on the plus side, you have safety, you have clear communication of intent, composability, and separation of concerns. On the minus side, you have less than pleasing compiler errors, difficulty with debugging, and potentially also performance degradations. And I should also add that the monadic operations in the standard library in C++23 are somewhat narrow in their use cases. But if you have a problem that fits their shape, they are super useful. Now, while the specific monadic operations in the standard library are somewhat narrow, the concept of functors and monads is much more widely applicable and much more widely useful. So consider this talk an invitation to rethink how you design code and get new tools into your design toolbox. Generalize the idea of using functors and monads, and you start seeing new ways to design difficult code. Now, if you're curious to explore, or just to want to deepen your understanding about the things that I talked about, here are the resources. So this is a link to the GitHub. I will also put it up at the end of the talk, and on it you will find the compiler error cheat sheet, benchmarks, slides, and all the code, plus bonus code for showing you how to write your own monadic wrapper and how to combine two monads, in this case the continuation and the writer monad. But that's not all, because I collected all the references and the resources I used creating this talk, and I listed them all with short comments. So you will find books and articles, you will find related talks, papers, and if you can't use C++23 yet, there are some replacement libraries that you might want to look into. Okay, let's look back at the 3 goals I stated at the beginning of the talk and see how we did. I've just shown you all the references that you can have, so I think you can, if you want to, you can dig in and spend a week or a couple of weeks. Check. We talked a lot about what functors and monads do. We've seen how functor magic can lift out common repetitive code, separating the what I do from where I apply it. So you can write a function once and then apply to single values, to vectors, to optionals, and to other things. Use monads to unwrap, and you can build pipelines that you could not build with functors alone. I hope I could give you a taste on how useful functors and monads are. And this is just a start. If you look at some of the links in my references, you will find out how much further you can take them. Check. And finally, we've seen examples of using the monadic operations of the standard library, and they are useful in some common concrete use cases. And you don't even need deep understanding of the theory behind functors and monads to use them. Please try them out, do your own measurements, make sure they do what you want them to do, and then apply them to new code if they fit your needs. Let's recap the patterns that we had. We have the ranges few monad for a pipeline where each step takes one input and produces n outputs. We have optionals maybe monad to build a pipeline where some or all of the operations may fail to produce usable result. Alternatively, std expected to provide useful error information in case of failure. And optionals default monad to grab the first usable result from a sequence of functions. These will help you write safe and readable code, the monadic operations in C++ 23. Thank you.